Hello everyone, this is Dr. G. Karthik Reddy, Associate Professor in the Department of EC, MLR Institute of Technology, Hyderabad. And the topic is Uniform and Exponential Random Variables. Today's content is Uniform Random Variable, definition of Uniform Random Variable. I am going to discuss about next. What is the formulation of Uniform Random Variable? Next. What are the applications of Uniform Random Variable? Next. Okay, example of uniform random variable. Okay, so with some problem we are going to discuss next. Similarly, in exponential random variable, what is the definition of exponential random variable? What is the formulation using the density function? Next, what are the applications of exponential random variable? Next, we will discuss problem related to exponential random variable. Next, finally, we will discuss the comparison between uniform and exponential random variable. We'll start with uniform random variable. What is a definition of uniform random variable? Okay, it is a one where probability of the random variable falling within any sub-interval of a given range is proportionally to the length of that sub-interval. This type of random variable is characterized by constant probability density over a specified range. For example, in graphical representation, we are going to discuss, for example, x. X is a random variable which lies between minus infinity to plus infinity. For example, at certain range, for example, I am considering A and B or the two instants of x. Okay, at that part, you are having the constant. Okay, you are having the constant probability density. Okay, here the function is probability density. Probability density is denoted by small fx of x. The value for this range is 1 by b minus a. 1 by b minus e. Okay. Here, for example, x is a random variable. In that some range a to b is one range. At this range, the probability density is constant. Okay. At this one mostly we are using in the application of where we are using in the quantization in PCM. Quantization in PCM, we are using the one of the major application of uniform random variable. Now next, formulation. Okay, what are the distribution and density functions of the uniform random variable? It is defined. Okay, what is the just now I discussed. The minimum range is A and maximum range is B. Here we are considering A less than B. Okay, defined by two parameters. A is the minimum value, B is the maximum value. Then what you are going to get, this is fx of x. Then at this range, the value is 1 by b minus a. Okay, 1 by b minus a, it lies between A to B. Then 0 otherwise. Other values are 0, 1. Now next, 1 by b minus a ensures that the probability defined over the interval A comma B, which is 1. Now next, similarly you calculate for cumulative distribution function. Okay, to calculate the cumulative distribution function, you know the formula. Fx of x is equal to integral minus infinity to x small fx of x dx. Just to substitute the small fx of x in this interval and you will get these three ranges. Okay, fx of x is defined 0 for x less than 0. The graphical representation is, this is A, this is B. Okay, we are having the slope range. Okay, this is, you can consider that x, this is x, this is small fx of x. Okay, x less than a, it is 0. Okay, here A to B, x minus a by b minus a. As x value is changing, the value is increasing. Then after that, it is 1. After x greater than b, it is 1. This is a mathematical representation and this is a graphical representation of cumulative distribution function. Okay, these two formulas are related to the uniform random variables. Now we will discuss one problem related to uniform random variable. Suppose a random variable x, okay, represents the time in minutes a bus arrives a station with 20-minute window, uniformly distributed between the interval A 10 minutes, B 30 minutes. Okay, PDF value, you know it, 1 by B minus C. B minus A, 30 minus 10, 1 by 20, it lies between. Next, CDF, you know that. Okay, CDF is defined between these ranges, that is a value. Then what is a mean? Mean, you have to calculate. Mean is equal to expectation of x is equal to integral minus infinity to infinity x into fx of x dx. Here the density function is defined only for a to b, x into 1 by b minus a into dx. 1 by b minus a is constant, take outside the interval, then x. X is equal to, here if you do the integration, x square by 2, a to b. Then what you are going to get? 1 by 2 into b minus a. Here what you are going to get? B square minus a square. If you further simplify, this is like a b square minus b minus a into b plus a by 2 into b minus a. Then you will get a plus b by 2. That is a plus b by 2 is the answer for expectation of random variable. Now next, variance. Variance, similarly you have to do it. First you have to simplify mean square value. Mean square value also same. Here x square. Here 1 by b minus a into dx. If you simplify, you will get mean square value. This is mean square value. Then what is variance? Variance is equal to mean square minus mean of square. If you substitute the values, then you will get the answer b minus a whole square by 12. This is the answer for variance. This is asking for the variance. Now next, okay, he is asking that probability of bus arrives between 15 to 25 minutes. If you want to arrange between the same procedure you have to follow, then you will get the 0.5 is the 50% chance that bus arrives between 15 and 25 minutes. Okay, probability of getting the chance is 15 to 20. This is a concept related to uniform random variable. Next, we are going to discuss about exponential random variable. What is exponential random variable? Where we are using this? Exponential random variable models the time between the events. Models the time between the events. Okay, there we are considering the count of events. Here between the events models the time, where our events occur independently and at a constant average rate, same like Poisson. It is widely used to model waiting times. Waiting times in a system like queues, reliability, survival analysis. These are the applications where we are using this. Okay, same concept which you are using for Poisson, but a slight change. Models the time between the events. Models the time between the events at a constant average rate. Okay, generally we are having the, okay, when you are taking the, this is a representation, so x, fx of x. Okay, here lambda you may have. Okay, generally fx of x, you are taking, this is a exponentially decaying curve, exponential random variable, just you are representing in this form. Okay, the different formulation you are having in the next slide. Okay, lambda probability density function represents fx of x is equal to lambda e power minus lambda x. Okay, for x greater than or equal to 0, means here we are defining this as a lambda. Next, okay, here you are having the fx of x. Here we are having x, lambda e power minus lambda x, 0 for x less than 0. Okay, x greater than 0 is a rate parameter representing the number of events per unit time. Now similarly for density, if you know the density function, distribution function is very easy to calculate. Just a formula, minus infinity to x. Okay, here what you are having, fx of x dx, where here x value is greater than or equal to 0, then what you are going to get, 0 to x, fx of x is lambda e power minus lambda x into dx. Okay, lambda is our, take outside, lambda 0 to x e power minus lambda x dx. If you simplify this, you will get 1 minus e power minus lambda x for x greater than or equal to 0, 0 for x less than 0. Expectation. How we can calculate the expectation of any random variable? You have the definition. Expectation, this is a continuous integral minus infinity to infinity x into fx of x dx. Just substitute 0 to infinity, because x is greater than or equal to 0, which is defined x into lambda into e power minus lambda x dx. Then if you simplify this, you will get the expectation of exponential random variable, which is 1 by lambda. And this is the variance. Variance, how we can calculate, you know it. First, if you know the calculation of mean, then we have to go for mean square value, which is again 0 to infinity x square into lambda into e power minus lambda x. Okay, if you simplify this, you will get the mean square value. Then what is variance? Variance of x is equal to mean square minus mean of square. Then you will get the variance, which is 1 by lambda square. Next, we are going to discuss about the problem related to the exponential random variable. The exponential random variable we are going to discuss. Then here the average number of customers arriving at a service desk is 2 per minute. 2 per minute. The time between the arrivals x follows exponential distribution. Okay. Here clearly I discussed in the definition that the models the time between the events, okay, occur independently at average rate. Same concept is applicable here also. The average number of customers arriving at a service desk is 2 per minute. 2 per minute, that is lambda rate parameter, that is lambda equal to 2 into e power minus 2x. This is the CDF 1 minus e power minus 2x. Mean value is 1 by lambda. This is the variance value. These are the different values or different parameters for exponential. Next, time between less than 1 minute. Time between less than 1 minute if you require. This is a x less than 1, fx1, substitute it, then x equal to 1. X equal to 1 if you substitute, then you will get less than 1 minute. There is approximately 86% chance the next customer arrives within the minute. You can calculate less than 1 minute, less than 2 minutes. So just substitute the value in x. Next, the comparison between uniform and exponential random variables. The definition tells that uniform random equal probability for all the values within the specified range. Here, models in exponential distribution, the models the time or distance between the events in a Poisson process. Okay, between the events, the models the time or distance between. Here fx of x is equal to 1 by b minus a. Okay, for a less than or equal to x less than or equal to b. Here fx of x is equal to lambda e power minus lambda x for x greater than or equal to 0. Then the CDF, capital fx of x is equal to x minus a by b minus a is for same interval. Here also capital fx of x is equal to 1 minus e power minus lambda x. Next, this shape of PDF is flat. Here exponentially decaying. Here the range is a to b. Here the range is 0 to infinity. Here the expectation is a plus b by 2. Here 1 by lambda. Here variance is b minus a whole square by 12 for uniform. 1 by lambda square for exponential for variance. Memoryless property. It does not have memoryless property. Satisfies the memoryless property. Next, applications. Random sampling, lotteries, modeling, okay, equal probabilities. Okay, in these cases, along with that, quantization also we are using in digital communication. Next, waiting times, reliability, survival analysis, the time between the events. This is for exponential distribution. Example, time uniformly distributed between 10 and 30 minutes. Here, time between the customer arrivals at a service. Okay, between the events is exponential. Constant, fixed specified range of the density function is uniform. Thank you.